Hey guys, the objective of this video is to find the settlement from our numerical solution. So I'm going to be finding the settlement at different times using the solution we developed in the previous video. So first up, we need to look at the formula for settlement. Settlement equals, so this formula is just for numerical solution. You wouldn't be able to use this in any other circumstance. So it equals mv, m subscript v qh minus m subscript v, the integral from 0 to h of u dz. It looks very hard, but it's very simple. We just need to define what all these things are. Q is equal to the applied stress at our time of reference. H is the layer thickness. MV will be given to us, it's a constant value. So for our case, MV will be 0.0004 meters squared per kilonewton, so this value will be given. U is the pore water pressure, excess pore water pressure. So pore water pressure is the excess pore water pressure, and dz is the layer thickness, or the subdivision of the layer. So not layer thickness, because that's we define there. So it's the divided layer thickness. So essentially what's happening, the way this formula sort of works, is that if we have our layer which we've subdivided, we're getting different pore pressures. So I'm representing these in lines. So that U1, U2, U3, U4, and U5. So these values are at different depths, at different changes in Zs. Okay, so on. So we're getting different pore water pressure values at different depths and at different times. So that's what this diagram represents. And this is at a fixed time equals whatever. It's at a fixed time. We're getting all these values. So what this part of the equation is saying is we're just integrating U with respect to Z. So we're finding the area. We're finding this area, and that gives us that part. We're not actually going to be integrating. To find this area, we're just going to be using the trapezoidal rule, which states that U0 plus UN, so the initial pore water pressure plus the final pore water pressure divided by 2 plus the remainder up to plus UN minus 1. All this times by the change in Z. So that is now that integral. And we've still got the MV out the front. So it's pretty simple. If we were to do an example, let's say we were interested at the 0.6 minus. So at the time equaling 6 minus, we wanted to find the settlement at that point in time. So we would come and look at our values for 6 minus, which is this column here, our pore water pressure values, and we would just sub it in our equation. So S equals MVQH, so MV has been given to us as 0.0004. Okay, I'm now going to factorize, okay, I want to factorize it. So 0.0004 times by Q, which is the applied stress at that point. So the applied stress at 6 minus, so a point just before 6 is 100 kPa. So the applied stress is 100 kPa. And the layer thickness, H for our case, was 4 meters. So this is 4 minus 0.0004 times by this trapezoidal rule. So that's going to be the initial plus the final divide 2. So the initial is 0, the final is 0. So it's 0 plus 0 on 2 plus the remainder. So plus 75 plus 100 plus 75. So plus 75 plus 75 plus 100. And this is all multiplied by the layer thickness. So change in Z, which in our case will just be 1 meter. So for some cases it might not be. It's very important to ensure that your change in Z value is there. It might have been 2 or 0.5. Always include it. Sometimes you just assume it's 1, but it's not. The change in Z value is important. It might not be 1. So if we were to work this out, we would get a value of 0.06 meters, which is the same as 16 millimeters. So at time 6 minus, a point just before 6, our settlement is 60 millimeters. If we were to now do time equals 6 plus, it would be the same thing. Settlement equals 0.0004 for MV. The applied stress now is 160 kPa for 6 plus. The applied stress is 160. So that's changed. but our layer thickness is still 4 meters. So that's changed from 100 to 160, minus 0.0004 outside of 6 plus. So the initial is 60, the final is 60. So it would be 60 plus 60 on 2, plus the remainder. So plus 135 plus 160 plus 135. And this is all times by 1, that's the subdivision thickness, and we would get an answer of 0.06 millimeters, which equals 60 millimeters. Now, these values are the same for time equals 6 minus and times equals 6 plus. It should make sense because we're actually looking at a point, although we've said it's 6 minus and 6 plus, it's still at time equals 6, and that settlement should be the same, which it is, and that's millimeters. If we were to do just one more, time equals 15, at the point 15, the settlement would equal MV. The applied stress at 15 is 100 times by the layer thickness minus 0.004 outside of the initial, so 0 and the final, so 0 and 0, so 0 plus 0 on 2 plus the remainder, so minus 5 plus 7.5 minus 5. So plus 7.5 minus 5 minus 5, and this is all times 1, the subdivision layer thickness. We would get an answer of 0.161 millimeters, which equals 161 millimeters. Now, if we want to look at when time equals infinity, so the final settlement, if we look at our equation, it's S equals mvqh minus mv, the integral of 0 to h of u dz. Now, because at time equals infinity, the excess pore water pressure will equal 0, as all the excess pore water dissipates from our soil profile, which means that this part of the equation will go to 0. So we're going to completely cross that part out for the final settlement. The final settlement will just equal mvqh. There'll be, this component won't exist because u is approaching 0, which means that our final settlement will be 0.0044 times q. So the applied stress at time infinity, this load is sustained for the rest of its life at 100 kPa. So that would be 100 times by h, which is the layer thickness, which is 4 meters. We would get an answer of 0.016, which equals 160 millimeters. Okay, don't be freaked out that the final settlement is less than the settlement at time equals 15. This is because it might still be recovering from this abrupt load increase. Anyway, guys, hope that's helped. That's how you find the settlement. It's just that formula where this integral is just the trapezoidal rule, and you would have to find the settlement at every single point. And you could also find the settlement by making this go to 0 because of the pore water pressures eventually going to 0. Hope that helps, guys.